Hello guys, today I'd like to talk about the Codeforces 687 and it is a Division 2 contest, and this video is a post-context explanation. You can say that in this contest I solved 4 questions, but for the first question I solved it pretty late. But I'm lucky because many people fail on the system test for this question. So I have a higher rank than the pre-test, and that is also my highest rating I can achieve. Yeah, you can see that. Okay, so before our starting, we will have an overview of the questions. So for the first question, it is pretty straightforward, and for the second question, it can be solved using the complete search or the brute force. And for the C problem, it can be solved using the dynamic programming. And for the D problem, if you can have some observation and you can reduce the constraint, and it then can be solved using the brute force. But I also have another solution which I used on the contest. It is a little complicated. And for the problem E, I think the key observation is that you need to model this question in another way, and then if you can write the target function as a math formula, and it will be easier to solve. Okay, that's all. Okay, let's start with the problem A. This question is about that there is a prison like a grid, and for each cell there is a prisoner, and there is also an exit like here, and so the question asks us to calculate the maximum time for every prisoner to escape. So it means that we need to calculate the largest distance between the exit and all of the cells. So we can say that it must be at some corner for these corners. So what we need to do is to calculate the horizontal maximum distance and plus the vertical maximum distance. So our code will be something like this. First is about the vertical maximum distance and the horizontal, and then we add them, and then we can get the answer. Okay, then let's look at the problem B. It can be solved using the brute force because the number of colors is very small, it is only 100, so we can just iterate of the color to see which color to paint. So this problem is something like that. There is a street and there are many houses with different colors. And let's paint it. Okay. And this painter can just paint a continuous segment of house into the same color. So if we want to paint black, and we can find the first house that is not black, then paint off this K house to the black, and then we go to the next house, or like this is red, so just paint off the K. Yeah, okay, it looks a little different because I want to show that if we meet some house that is already black, then we can just skip and find the next one that is not the black. Okay, then we will do this process for all of the colors. So our code should be something like that. First, we find all of the colors and insert them into a set, and for each color, we will, if we find some house that is not that color, then we will plus I to the K and increase our day by 1. And if it is already that color, then we can just skip that. So then finally we can get our answer. Okay, now let's move to the problem C. It is a dynamic programming problem, and since we don't know how many platforms to delete and how many platforms to add, so we will iterate off the cases for the first platform. So it means that if the P is equal to 2 here, and we will jump to the third platform as the first. So it means that we will delete the first platform. Okay, then if we already decide which platform as the first platform, and then the all following process will be deterministic. And we can also calculate the cost for adding the platforms. Okay, so we can get our DP state. Let's call it DI. It means that if we can jump to this to ice platform, then the cost for following is DI. And we can say that it can be calculated from the back to end, because if we already calculate, let's say this is DI, and for the DI minus K, it is its previous move, and for the DI minus K, it can use the result of the DI. So it can be calculated from the back to the front. And it is noticeable that for the last K elements, they should be the base case, because they are the last move. Because if you can arrive on any of these platforms, and then you just need another step, then you can finish. So those K elements are the base case, and then we use this base case to calculate all for the previous DI. Okay, so if we already finished this one, and then we can just iterate from the piece platform, since it is the first platform, and from P to N, we can choose all of them as the first platform, and use them to add the DI. Then we can get our result. Okay, so let's see the code. First read off the elements, and here I add some character at the head to this string, because so the index will from 1 to n. And here is our DI, and we will start from the back. So if this platform is empty, and then we need to add one, and we need the cost is s. And for the second, if this platform is not the last K platforms, then we can use the previous platform. If it is not in this if, then that will be the base case. Okay, then we get off the DI. So let's calculate the total cost, which we will plus the deletion of the platforms at the front. So from the P to the N, and we need to calculate how many platforms we deleted, and then multiply it by y, and then plus DI, and take the minimum of all of these possible results, then we will get our answer. Okay, now let's look at the problem D. It is something about the bit manipulation, and let's look at the first example. Since it is about the bit, so we will write all of the numbers in the binary format. It is 2, and it is 5, and 6, and 8. And we can see that from this example, it is not easy for us to see which two numbers we need to combine. And another thing we can do is that we can group off those numbers by the most significant. We can call such a group level. And we can ask ourselves that how many numbers can in each level. we can see that if there are at least 3 numbers, and then we can always combine the greater 2 numbers, and their most significant bit will cancel, so it will smaller than the previous one, and then we are done. We just only need 1 step to reach our target. Okay, so let's see our constraint. Our A is smaller than the 10 to the 9th, and we know that it is about 32 bits totally, and since each level will have no more than 2 numbers, so it means that our n will not greater than the 32 times 2, that is 64, and that will decrease our constraint on the n pretty much. So then we can use brute force to check off for those XOR combinations. Okay, so that means that we will define interval called from left L to K. It means that XOR all numbers in L to K. That means the index from L to K. Okay, then we want to find those 2 segments. One is L to K, and another is K plus 1 to R. And we want the left one is greater than the right one. So that is our target. And we can use brute force to check off them. And this algorithm will be On to the third. Okay, so let's see our code. So first we will use the map called level to record how many numbers in each level. We will use the built-in function to count the leading zeros. And if something is the 3, and then it means that we can only finish it with 1 step, then we are done. Okay, then if we are not done, we will check off the L and the left bound and the right bound, and the interval count. And here the first is the XOR of the L to K, and the second is the XOR of the K plus 1 to the R. And here we use the prefix XOR, so we can get this result in one time. And if it will satisfy our target, and we will record how many steps we used, and we take the mean of all of them, and then we will get our answer. Yeah, if there is no answer, we will output the -1. I think the most interesting in this problem is that with our observation, we can reduce our constraint largely with some property of the bits. It is just 32, and I think this property may also can be used in the future questions about the bit manipulation. Yeah, that's all. Okay, and I'd like to introduce another way that I used in the contest, which is pretty different from the one in the editorial. And in my way, that is an ON solution, and it is also our greatest solution. And I think maybe the advantage of my solution is that if there are much more than 32 bits, and it can compute the result quickly. But the disadvantage is that there are many cases we need to consider. Okay, so let's begin. Okay, so similar from our previous key observation, that is, I will write off the observations here. First is that no more than 2 numbers on each level. Okay, And if there are more than two numbers, then we just need one step, and then we are done. Okay, so it means that we're only interested to the combinations when each level have two numbers. Okay, so I think that we can think from the largest number to the smallest one. So assume that there are two numbers on the same level, and what we want to do is to XOR them and then pass through it to the next level. And we can, because when we XOR them and their most significant bit will cancel, and then we can see whether our result is smaller than the next one. So that is our first compile. So XOR higher level, then compile with the next number. Okay, and okay, so let's see what will the result be. For example, if our result is have 3 bits, something like this one, and it is easy to say that if you XOR it with some numbers that have lower level, and their result will also belong to the higher level. So we don't need to pass through it because it will always be larger. It will always belong to the higher level. Okay, so if it have higher level than the next number, we can just through it. And then the second case is that it will have the same level than the previous one. Then it is what we are interested. And there are also several cases. For example, if there are already two numbers on that level, and so now we have three numbers on that level, and then we just only need one more step to reach our goal, and we are done. Yeah, so that is a termination case. Let's write this one. If result has a higher level than next number, then through it. Okay, if result has the same level, but now there are total three numbers, we are done. Okay, so if we already consider all of these cases, and the cases left is that when we pass our result to the lower level, but there are still two numbers, and what we need to do is something as previous what we have done, and we just combine them and pass them to the next one. So something like we just do it recursively, but and each number will be visited at most once. Okay, and it is noticeable that when we want to see whether there are two numbers, these two numbers will larger than the next one. Actually, there are two cases. Let's call this x, y, and z. And we want to compare x or y is smaller than z. And actually, there is also another case, which we can find in the example. Another is x is smaller than the y, x, or z. and actually they are pretty different, and we need to check both of them. So check both. And x smaller than the yx over z. Okay, I believe that someone may ask why this way is optimal. Like if we now have something like we have two numbers in the same level and another number in the next level. And why don't we just combine those two numbers and pass it to the lower level? Because it will contradict our three observation. Because you can see that the XOR of these two numbers will always have a higher level, and it is meaningless to compare it with the lower one because it will always be larger. Okay, and another corner case I meet in this problem is that, for example, if the 111 is passed from the higher level, and we can see that there are three numbers in this level and we are done. But one thing we can't miss is that we still need to XOR those two original numbers and pass it through the lower levels. We can't miss this case. Okay, now we can look at the code. Okay, now let's walk through the code. I know this code is pretty long, and I believe no one likes to read out others' long and complicated code, so you can just skip this part if you don't like that. Okay, let's start. So as previous, we use the map called the level to record how many numbers in each level, and use the index to iterate the start index in the reverse order for each level. So it means that if there are different levels and we want to record the first element in the reverse order, so then we can iterate through those elements in one order easier. Okay, then these are all the same as previous. We check whether there are three elements in one level. And here the before means the element that the number that passed from the upper level, and the step is the steps count. And here is the answer. And we will iterate through the level order, not the element order. Okay, and we can see that there are so in the first if statement, it means that there are no elements that passed from the upper level. First case is that before is -1, it is the initial number, and another is that the before element has more leading zeros, which means that that is at the higher level. So that is our the rule 3. We check that here. Okay, and we see that if at this level there is only one number and we can't do any XOR, and then we will just start a new process. We will reset our step and before, and we continue to the next level. And another case is that there are two numbers in this level, and we will record them, and also the index of the previous number. We didn't directly write something like a -2 because we are not sure if that exists. Because maybe the second here is already the first element, then there is no element before it. We will check that later. And in the else statement, it means that there is one element that passed from the upper level and that is also valid. So when there are already two original numbers in that level, so now there are three numbers now, and we will record the result. And reset the before, but we will also increase one for that step because we will do the XOR here, because as what I said before, even when we find some levels that have two original numbers and one upper element, we still need to calculate the original numbers and pass it to the lower levels. So here we record those two numbers, and here is the case that there is only one element. So plus the one that passed from the upper, now there are two elements, and we will record them. Okay, and here is the process to compare, and that is the rule 5 here. We will call the XOR of the greater two elements as the high, and we can say that if the pre is larger than 0, so it means that there is also an element that is in the lower level, and we XOR them as the low, and we will try to compare those two situations, and if one of them satisfies, so it means that we find that solution, and we will record it the steps, and we will reset. Okay, here the question is that we reset because we don't want to pass the high to the want to pass high to the lower level, because the high is smaller than the A previous, but it is also possible that the low is greater than the first, so we go into this if statement. But actually, as what we said before, we only want to XOR the numbers in the same level. For example, that is a bad example. So we only want to compile these two numbers and pass it to the lower level. If we compile those two numbers and pass, and this result will always be greater than the lower level, then that will also contradict our third rule. So we don't want to pass that. We only want to pass the valid XOR of the same level. Okay, so here we just reset, and here we will pass that to the next level. Yeah, and that is the overall pipeline, and for the final solution, it will be the same as our brute force way. And one interesting thing is that from this way, we can see that in the brute force way, we check off the LK segment, but in this way, we can show that the length of the LK is not greater than 2. And I also tried that in the brute force way, and that will satisfy. So I think it is another observation, and it may give some like lower time complexity, but that is not necessary in this problem. Okay, finally we go to the problem E. I didn't solve that on the contest, but after I reading the editorial, I think it is pretty interesting. So there are two problems for us. One is that how can we reorder of those bosses, and another is that how can we choose those k restart times. So let's think this problem as following. If the k is 0, then it is obvious that we need to sort off the bosses in the non-increasing order. Non-increasing order, so it is from the largest to the smallest, and somewhere it may be the 0, and then we can just calculate the prefix sum of all of them, because we don't need to choose the restart time. Okay, then if we are going to consider the case that k is not 0, then I think that we can also sort our of elements in the non-increasing order and then calculate the prefix. So it will be something like that. For example, here is the real row, and we want to calculate the prefix sum. So our prefix sum should be something like, yeah, like this one, because it will increase rapidly because the largest elements are at the very beginning of this sorted array, and then it will go to decrease because there is some negative element, and at some time it will decrease to negative. And what we need to do is to calculate the area of this 2 plus the positive area and the negative area, and it is something look like the integration. And for all of those k restart point, we need to choose some k restart point. So the area we need to calculate is the those triangle or something that's similar to triangle in this graph. Yeah, so what we need to do is to minimize those green area using the k restart point. But actually, I think it is not the right way to model this problem, because you can't go further with this graph. Okay, so with the editorial, actually we need to model all of the bosses as k stacks, k plus 1 stacks, and we will place all of the bosses at the sum of here. We can model it as the k plus 1 stacks because for each stack it will start at the 0, and all of the following process will be the same. Okay, then let's see what will our final bonus point will be. Let's print it with the red. Okay. So for each stack, if there are x bosses on one stack from a1 to ax, okay, then their total sum is equal to for the a1 is the top one, and the ax is the bottom one, so it should be the x minus 1 plus a1 and the plus x minus 2 times times a2, and plus finally it is 0 multiple ax. Yes, because for the last element it will not be added to the bonus point. Okay, then there is another observation. If there are two bosses at the different at a different level, we'll call its head as the level. For example, this one is the -5, and this one is the -3. And from our formula, we can say that they will have the different weight, like the different head. So we can always get an optimal, a better solution with swapping those two elements. If we swap that, because like if this will multiply the 4 and this will multiply the 3, we can say that if we always make the smaller element multiply the smaller weight, it will also be better. Okay, so that is another observation. So it can give our some hint on how to place those elements. Then we may think that we can place them from the smallest to the biggest, and we want to flatten them. We want to make the head as small as possible. So for example, we place the -5, -4, and -4, and -3, -1, like this one. And because with this organization, and our height will be as small as possible. But there is also some elements with the positive value, like the time, time, 9, 5, and 1, and even some -1. Because the prefix of them is positive. The prefix of them is positive, so we also want them to appear as small as possible. So for all of these elements, we want to make it as high as possible. So we will just stack all of them on the same stack. So it means that we will move all those stacks to the highest stack if we already place off the negative elements. And the negative elements here, I mean that is the one that the prefix is negative. Let me write here. Elements means prefix sum is negative, because as what we have observed previously, we just want to minimize the area that the prefix is below the 0. We just want to minimize this part. Okay, so then we can get one of our solution. So let's look at the code. Okay, so first we need to start off them in the non-increasing order. Then we calculate the prefix sum. Then we need to find the element where the prefix sum is negative. So we will divide off the elements in two parts. One is that we need to stack as high as possible, and another that we need to flatten off them. So first, for the flatten the negative elements, and for this part we are calculating the index from the end, then divide by all of the stacks. So we will get which level that elements belong to. And here we need to calculate the highest stack for all of those negative elements. So here the two exclamation means that those two exclamation marks means that it can convert all of the positive number to 1 and 0 still to 0. So it means that when the remainder is 0, for example, if there are 6 negative numbers and there are total 3 stacks, so the highest stack should be 2. But if there are 5 total number and 3 stacks, so the highest still be 2. So it means that when the remainder is not 0, then we need to plus 1. Yeah, that is the intuition between that. Okay, so then for the positive prefix sum, and we calculate the level for each element, and then multiply them, and then finally we can get our answer. And there is another we introduced in the tutorial using the priority queue. I think the basic idea is equivalent to our previous method, but it is much easier to implement it, and it is also pretty genius. So let's look at the code. So the basic idea is that first start off them in the non-increasing order, then we will initialize k plus 1 stacks with all of them are 0. And then we will take the biggest elements in the priority queue every time and add that to our answer, and then add the CI to that element, and then push back to the priority queue. Firstly, it will process the largest element first. So at the very beginning steps, when the prefix sum is positive, so it will all stack on the same stack. And then when it becomes negative, so it will choose the largest one, and that should be 1, 0, and add the negative number to that stack. And finally, when all of them are negative, then it will choose the largest negative. And the largest negative, so finally it will also do something like what we have done previously, like flatten those stacks and add the positive stack on one of them. Yeah, so they're equivalent, but it is pretty genius, and I'm pretty surprised to see that many accepted solutions on the contest are using this method. So that is pretty amazing. They can think this on the contest. Oh wait, I need to add something to the last method, because when I think carefully of it, I think the proof is not obvious at all, and it needed to use the induction hypothesis. Okay, let's look at this example. We can see that at the very beginning, when the prefix is positive, and all of those elements will stack on the same place, until there is a negative prefix. We can see that here the prefix will become the -1. So all of the sum on that stack should be the -1. And it is easy to say that when we replace all of this prefix with the sum of them, the -1, it should also be the largest element in the following sequence. Because the sequence is sorted, and we can say that the -7 should be greater or equal to all of the following elements, and now it will add some prefix that is greater or equal to the 0. So of course it will be larger, so it will also be some negative elements that is greater than all of them. So in other words, it is still sorted. Okay, so let's simplify our problem. We can just replace all of this prefix with this sum. That is -1. And for simplicity, we just replace all of the negative to the positive one. And in the following operations, we just take the minimum of them. So that will be equivalent to the previous operation. And there's another constraint is that we want to flatten all of the boxes as most as we can. So it means that we don't want any two stacks that one stack will have more than two boxes than another one. So it means that the maximum and the minimum height of these k stacks cannot differ by more than one. Okay, so let's write our problem like following. Given a sequence of boxes with sorted heights in non-decreasing order, we want to place them on k stacks every time we will pick the stack with lowest height and place. Let's call the height of the boxes as the C. Place CI box on it, and we want to prove that. The let's call maximum and minimum numbers of this k stacks cannot differ by more than one. So here we define that stack have two property. One is like what is the height of that, and another is that how many numbers of boxes on it. Yeah, so this is our system of problem now, and we want to prove it. And we can see that the case that we don't want to see is something like that. For example, these are two stacks, and they have the same number of boxes on them. For example, they all have n boxes on them. And let's call this AI. AI is height, and the AJ is another one's height. And now we will add another box on the AI, and let's call it CI. And we don't want to see that the AI plus CI is smaller or equal to the AJ. If AI plus CI smaller or equal to the AJ, if that happens, then it means that we can add another box on it. So then those two stacks will differ by more than one boxes, and we want to prove that it is not possible. That is not possible. So it is so if we can prove that, if all stacks with numbers of n plus 1 always higher than stacks with number of n. Okay, so if we can prove this statement, then it means that So every time we will choose the stack of the n boxes and plus it by 1, and then our minimum will be some other stacks with n boxes, and we just pick and we just place all of the boxes until all of the stacks have the same number n plus 1, and we will stack one of them to plus another box, and if it is true, then we can say that the statement that we want to prove previously is also true. Okay, so what we want to prove is this statement. So we will use the induction hypothesis. And let's first think about the induction step. We will consider the base step in later. Okay, so assume that now we are placing Ci to the lowest height stack, and all of the stack before this step all satisfy this statement, so all of them are true, and that because that is from the induction hypothesis. And so assume our current stacks have number of boxes n and n plus 1. Okay, so from this statement we can see that the minimum height stack should be some stack that has the number of n, right? So we will just pick the lowest height stack, and then what we want to prove is that if we add Ci to, let's call the stack with the lowest height as the Ai, same here, and any other stacks with the number of n, call it Aj. If we add Ci to Ai, then for any other Aj that has n number of boxes, it satisfies that it will satisfy that Ai plus Ci that is greater than the Aj. Okay, so let's see how to prove this one. We can actually let's take the top box on the Ai and Aj separately. Let's call it Bi. It means that a box with the height of the Bi, and this is Bj. So we can see that for this stack, actually there are I minus 1 boxes, and for this stack there are also I minus 1 stacks, and from this statement we can say that so the Ai actually has n boxes, right? So this stack will be higher than this stack from this statement with the induction hypothesis, right? So let's write this one. We can say that the Ai is greater than the Aj minus Pj. And another thing we can see that is since the BJ is placed previously than the CI, so we can get that CI is greater or equal to the BJ. Okay, then if we already have this statement, then we can just add them, and we can see that AI plus CI is greater than the AJ. So it means that our new stack means that the new stack with the number of n plus 1 will be higher than any other stacks with the number of n. Okay, so our induction step is proved. Let's write this. Okay, it is our induction step. Okay, then let's think about what is our base step. Since that in the induction step, we use the assumption that we can take out the top box, meaning that the BI and the BJ here. So it means that if we want to do the induction step, there should be at least one box. Okay, so our base step would be something like that. When we place the first layer of boxes on all stacks, it will also satisfy that statement. And it is easy to say that it is true because initially all of the stack have 0 boxes, and when we place the boxes in the sorted order, then it is easy to say that every stack will be larger than the positions that there is no boxes. Okay, so since we can prove all of those 2 steps are correct, then we can get our answer. So yeah, so it is proved, and it is not obvious, so I hope this can help us to understand.